Here is the fifth structural design pattern from the Gang of Four book. This one is called Facade Pattern, and it is a pattern you use when you need a simplified, high-level interface to the functionality of a complex, low-level subsystem. I'll start with a quick summary of what we are trying to accomplish with this pattern. The facade pattern is a good choice when you are trying to accomplish the following. You want to provide a unified high-level interface to a set of low-level interfaces in a subsystem. You want to make the subsystem easier to use. You want to wrap a complicated subsystem with a simpler interface. Let's go through the points. The key point here is that you have a complex subsystem somewhere in your application architecture. This subsystem will consist of many low-level components, and you interact with the subsystem through a large number of complex APIs. This kind of subsystem offers an enormous amount of power and flexibility, but it can also be very hard to use. You will need detailed upfront knowledge about the architecture of the subsystem to be able to use it efficiently. So, what do you do if you have to expose the subsystem to a large group of developers? The steep learning curve of the subsystem will be a major impediment to adoption, and there's a big risk that some people will use the API incorrectly and introduce bugs into the system. The facade pattern solves this problem. It encapsulates the subsystem within a single interface object. This object provides a high-level interface to a narrow domain of the subsystem. So instead of having to make a sequence of complex API calls, developers can now simply call the high-level facade interface. The facade will then make all the correct low-level calls into the subsystem to get the work done. The facade pattern offers a number of benefits. By using a facade, you dramatically reduce the learning curve to successfully interact with the subsystem. Developers are no longer required to master the entire low-level API. Instead, they only have to familiarize themselves with the high-level facade interface before they can get started. This will significantly speed up the adoption of the subsystem. The pattern also promotes the decoupling of the subsystem from its many clients. The high-level interface effectively masks the details of the low-level subsystem API, which means that you can make sweeping changes to the subsystem without having to worry that the client code will break. However, the facade pattern also has a number of risks. The biggest risk is when the facade is the only access point to the subsystem. Remember that I said at the start of this lecture that the subsystem API offers an enormous amount of power and flexibility. All this flexibility is gone if clients are forced to use the facade to gain access to the subsystem. But exposing the subsystem to clients is also not risk-free. An exposed subsystem removes the decoupling between the client and the subsystem, which means that your freedom to change the subsystem API is significantly reduced. And finally, a facade can quickly turn into an anti-pattern. If the subsystem covers, say, more than 90% of your application architecture, then the facade effectively becomes a God object. This is an all-knowing and all-seeing master object that controls every aspect of your application. This is an anti-pattern because it completely removes all of the flexibility and power that you get from an object-oriented language. Almost all of your business logic is now in a single object. This is universally recognized as a very bad idea. Here is the UML diagram of the facade pattern. As you can see, the diagram is very simple. We have a complex subsystem consisting of many components with low-level APIs at the bottom of the diagram. And above the subsystem is the single facade class that wraps the subsystem and provides a high-level interface to its clients. The facade is a single object instance, and therefore it is often implemented as a singleton or a static class. Let me show you an example of the facade pattern. I am going to write a simple program for a bank to set up a mutual fund. Mutual funds are investment products where every month your bank deducts money from your bank account to buy a certain number of shares on the stock market. My application architecture has a subsystem for interacting with bank accounts and stock portfolios. The subsystem provides a low-level interface for buying and selling stocks, getting current stock prices, making a withdrawal or deposit on a bank account, and performing a credit check on a given customer. Every month, the bank has to perform the following process for each mutual fund. First, get the current share price of the stock. Then, check if the bank account has sufficient credit to buy the shares. Then, withdraw the required amount from the bank account. And finally, use this money to buy shares. I am going to wrap this process in a single method of a facade object. I will implement the pattern with the following classes. Okay, let's take a look at the code. Here is a class called bank account, which will act as the abstract base class for any concrete implementation of a bank account. The class defines the abstract methods deposit, withdraw, and get balance for respectively depositing money, withdrawing money, and checking the balance of the account. And here is a concrete subclass of bank account called cash account that implements all the abstract methods in the bank account class. There's also a class called equity, which acts as the abstract base class for any concrete implementation of an investment product. The class defines the abstract methods buy stock, sell stock, and get price for respectively buying stocks, selling stocks, and checking the current share price. There is one concrete subclass of equity called stock, which represents a stock that you can buy or sell on the stock market. The class implements all the abstract methods in the equity class. To automatically create the right kind of equity, I added an equity factory here. The equity factory follows the singleton pattern to return only a single instance of the factory. And it has this method here to create new equity objects. As you can see, the current implementation can only create stock objects, but you could easily enhance this to also support index funds, real estate funds, and other financial products. And finally, we have the mutual fund class here, which acts as the facade to the banking subsystem. The class provides a simple buy method that implements the entire mutual fund process. I only need to provide an account number when creating the object, and a ticker symbol, and the number of shares when calling the buy method. All the details of accessing the bank account, creating the right kind of stock, checking the balance, and so on is done internally in this class. So the mutual fund class effectively acts as a facade and shields the implementation details of the stocks and bank accounts subsystem from the outside world. Finally, here is the main program method. It uses the mutual fund facade class to buy 10 shares of Apple using a cash account. Let me run the program to prove that everything is working correctly. I am compiling the code now. And I'm going to run the code now. Here we go. And there you go. I now own 10 shares of Apple stock. Everything is working. Here is a quick checklist you can use to implement the facade pattern. First, identify a complex subsystem in your application architecture that you want to simplify. Then, design a simple unified interface for the subsystem. Create a facade class with the simple unified interface. Have the facade call the appropriate low-level methods of the subsystem to implement the interface. And finally, modify the client to always use the facade. And here are some final comments. The adapter and facade patterns are very similar. Both patterns make changes to an existing interface. But the difference is in the intent of the pattern. An adapter changes a legacy interface to make components compatible with your application architecture, whereas a facade wraps a low-level subsystem interface with a high-level interface to reduce the learning curve of the subsystem. So the difference is in the intent, making something compatible versus reducing a learning curve. Another difference is in instantiation. A facade is often a singleton because it wraps one subsystem, but adapters are usually instantiated for every component they wrap. And finally, consider this scenario. You have a subsystem for creating sets of related objects. Does that remind you of something? Exactly, the abstract factory. You can view an abstract factory as a kind of facade for object creation. So, in this scenario, you could also use the abstract factory pattern instead of the facade pattern. Okay, let me conclude with a summary of what we have learned in this lecture. The facade pattern provides a unified high-level interface to a complex low-level subsystem to make the subsystem easier to use. The pattern promotes the decoupling of the subsystem from its clients, but denying clients access to the low-level interface also reduces power and flexibility. Facades can evolve into a common anti-pattern called a God object. Adapters and facades differ in their intent. An adapter makes legacy components compatible, whereas a facade reduces the learning curve of a complex subsystem. Facades are often singletons, and you can sometimes use an abstract factory in place of a facade.